Hello and welcome to a quick lesson on parametric equations. When we talk about parametric equations, we're looking at equations that are used to describe x, y, and possibly z coordinates of a point separately as a function of a third variable, typically t for time. That third variable is called the parameter. And they are especially useful to model time-dependent motion in two dimensions. So you'll see some of this in physics. Okay, so let's look at the graph of these parametric equations. We see that the parameter is again t. We have two variables, x and y. If we use the values from -1 to +2, we're going to make a t-chart here starting with -1. The x becomes -2 when you plug in, and the y becomes 6 when you plug in. 5 minus -1 is +6. And if we plot that point, we get a dot there. Next, we take all the values. I'm just using integer values, but with the less than or equals, we're obviously using all values between -1 and 2, so we'll be connecting these dots. But what happens is we get the point 0, 5 and 2, 4. And then lastly 4, 3. And what's happened is we now have a line segment, a directed line segment. Actually should have arrows showing the direction that it's going, because as t increases, the x increases but the y decreases. Okay, so that's the graph of the parametric equations given above. Try this one. We have -1, x becomes -1, y becomes -1 squared, which is +1. And if we plot that point, we get -1, 1. The remainder of the values, 0, 0, 1, 1, and then 2, 4. Okay, and recognizing this as a quadratic, I'm going to curve a bit. And again, there's an arrow showing the direction, as well as endpoints here, because we're not allowed values less than -1, so that puts a boundary on it, and up to +2 for t. All right. Moving on, graph these parametric equations by hand. You should notice there's a squared term, and you might expect, as in the previous problem, we're going to have some parabola shape. In this case, however, after we've plotted these points, -1, and then the remainder of them, 0, 0, 1, 1, 4, 2. Notice this parabola, or portion of a parabola, is horizontal. And again, the order is going to start at 1, -1, and little arrows to show the direction. Okay? And now we're going to approach the same problem, only we're going to give the words, create the parametric equations, t-chart or 3-chart, and then we're going to sketch it and see if we actually move right 1 up 2. And we're starting at the origin for the previous graph. So from the origin, we want to see if we go right 1 and up 2, somewhere in that area. Okay. Well, if we shift right 1, we have to consider this being coordinates, and we're going to add 1 unit. We're not going to put it inside parentheses here, so it's outside. We just add 1. And to go up 2, we're going to +2. to all the y values. And if we plug these values in, we see -1 squared is 1, 1 plus 1 is 2, and so on. The y values are 1, 2, 3, and 4. If we plot these points, we get 2, 1, dot there, 1, 2, the dot that we'd hope to hit. Hopefully that's our vertex. Go to 2, 3, that's going to be up here. And then 5, 4. So now we start to stretch out a bit. 5, 4. And that graph is going to look something like this with a direction where t is increasing. All right, so that's the idea on parametrics for graphing them from either words or the equations. And now we'll try converting from parametric to rectangular equations. In this case, we're going to start with equations x equals t plus 4 and y equals t squared minus 6. You should look at that and think that might be a parabola. If we use -3 as our smallest value, we get x and y values of 1, 3. And continuing through from -3 all the way to +3, get quite a list of numbers here. And if we were to plot those points, we would see these values. You see 1, 3, 2, -2, 3, -5, and so on. Just by looking at the graph, it's fairly obvious that the y values decrease down to -6, and then they increase from there. So 4, -6 should be our vertex, and sure enough it is. If we were to connect these dots, we would see starting from t is -3 all the way up to t is 3, we get a parabola. Looks like this. And in fact, our values go for domain from 1 to 7, and the range from 3 to 3, or actually I should say -6 to 3. And if we wanted to do something that will look a little more familiar, we have a way of eliminating the variable t, the parameter, and creating y as a function of x, not necessarily of just t. So we're going to start by eliminating the t from the equations. Initially, we're going to solve for t. So if you look at x equals t plus 4, we simply, give myself a note, solve the x equation for t. We're going to subtract the 4 from both sides. We get t equals x minus 4. That's useful as a substitution that we can make. That t is now a function of x. We can substitute that in where we see t, and we can get y equals x minus 4, the quantity squared minus 6, and we can stop right there. We should recognize this as a parabola shifted right 4 and down 6. And sure enough, if we look at our graph, it is right 4 down 6 from the parent function y equals x squared that has an origin at 0, 0. Okay, no stretches or shrinks yet. Let's take a look at the last problem with the use of a graphing calculator. In this case, on the graphing calculator, there are a few modes, and rather than being on function, you go down to PAR. That's code for parametric. In parametric mode, when you hit y equals, you get a very different looking screen than you're used to. You get this guy. And I've already entered the equations I want to do. X equals t plus 4, y equals t squared minus 6. And I've already got the interval. Let me show you how to set up the interval. You hit window, and again, that looks different. For the window, you're going to use t, which is the parameter, the now independent variable, and you have two dependent variables, x and y. And those are created out of plugging in the t values that are given. And finally, if we wanted to look at a table, the table is going to look a bit different. You hit second graph, and you get a table like this. And I've got it right here. You can see from -3 to 3, I've got x and y values, and we've shown how to graph those. So to graph on a calculator, graph has definite endpoints because it was only calculated for specific values of t. It's continuous. It fills all values between -3 and 3, but it doesn't go any further beyond that. And the graph has directed speed, so we would put arrows on it to show the direction it was plotted as the t increases. So if I went ahead and hit graph, I would get a graph that looks something like this. You'll notice that its scale is by 1, so if you count right 4 and down 6, the vertex is at 4, -6. We would have assumed that just by looking at the parametric equations. also from the y as a function of x. And we should put some arrows in there. It did, if you looked at that data table, x increased, so we would have arrows something like this. But definite endpoints here and here. Okay. Why don't you try this on your own? Go ahead and look at the previous example. See if you can predict some of the things that should happen. Write y as a function of x or in terms of x and see if your graph matches the transformations you'd expect. And we'll see you in class.